Today we talk about solutions, how they form, what they are, how we calculate their concentrations, and how we can apply all of that. So let's go ahead and jump into our PowerPoint and talk about solutions. Okay, so first we need to kind of talk about what a solution is. So a solution is a homogeneous mixture of two or more substances. So this can be a solid and a liquid. It can be a liquid in a liquid. It can be a gas in a liquid. It can even be a solid in a solid or a gas in a gas. They're just mixtures of two or more pure substances. The essential piece of a solution is that the solute is dispersed uniformly throughout the solvent. This means that the characteristics of a solution are very consistent throughout the solution. All of those macroscopic characteristics are the same no matter where you sample it. So how does a solution form? In order for a solution to form, the solute has to be pulled apart by the solvent and then solvated by it. So there are two things that have to happen, or three, I guess. First, the solute particles have to separate and the solvent particles have to separate. So that means that the intermolecular attractions within the solute and the intermolecular attractions within the solvent both have to be broken and pulled apart. Then new attractions have to form between the solute particles and the solvent particles. So this means that in order for something to dissolve, those new attractions need to be pretty strong. They need to be strong enough, in the case of dissolving an ionic compound, to actually overcome the lattice energy of the salt crystal. So, what affects solubility? We use this phrase, like dissolves like. And what we mean by that is that polar substances tend to dissolve in polar solvents, and non-polar substances tend to dissolve in non-polar solvents. And that's because in order to pull apart those particles and then replace those attractions with new ones, they need to be strong enough to overcome. And so generally speaking, if they're similar, they're going to be strong enough. So the more similar those intermolecular attractions are, the more likely one substance is to be soluble in another. So we use that axiom, like dissolves like. But on the AP exam, you can never simply write like dissolves like. You have to talk about the type of intermolecular forces between the solute particles and the solvent particles. So for example, why does iodine dissolve poorly in water but well in acetone? So let's think about the types of intermolecular forces. So iodine is a nonpolar molecule. So as far as its attraction to other iodine molecules, that's going to be exclusively London dispersion forces. Water, we know, is an extremely polar substance. And so it has strong intermolecular forces, in fact, even has hydrogen bonding with other molecules of water. So in this particular case, the iodine is relatively easy to pull apart, but the water molecules are not. And so these weak attractions that iodine has for water, which are only London dispersion forces and dipole-induced dipole, aren't enough to really overcome the attraction of water for other water molecules. Therefore, iodine doesn't dissolve well in water. Acetone, on the other hand, is a nonpolar substance. And so it's not strongly attracted to other molecules of acetone. And so the iodine is able to mix in easily and dissolve. So the difference here is the attraction of the solvent for itself with water is very strong, and the attraction of the solvent for itself with acetone is not particularly. So We would say, if we were asked this question on the exam, that iodine's intermolecular forces are more similar to those of acetone than they are to water, and therefore acetone dissolves better in a nonpolar solvent. Sorry, iodine dissolves better in a nonpolar solvent like acetone. So let's take a quick look at an example. So we want to label whether each of these following substances will dissolve better in water or in acetone. And so the first thing we have is methanol, which is CH3OH. And because we have here a hydrogen attached to an oxygen, we can see that this molecule is going to have hydrogen bonding, which means that it's going to have very similar intermolecular forces to water. So it's going to dissolve better in water. Sodium chloride, here we have an ionic compound that's always going to dissolve better in a polar substance. So an ionic compound like sodium chloride is going to dissolve better in water. Now we have bromine, which, like its friend iodine, is a non-polar substance, and so it's going to dissolve better in acetone. And finally, we have carbon dioxide. And carbon dioxide is also nonpolar because of its linear shape, and therefore it's going to dissolve better in acetone. That's not to say that carbon dioxide doesn't dissolve in water. It does, but not very well. It's going to dissolve better in acetone. All right, so now we understand what will dissolve in which solvents will dissolve in which solutes. I just said that backwards. Which solutes will dissolve in which solvents. Let's talk about what happens when they do dissolve. So we're going to talk about this idea of electrolytes and non-electrolytes. So an electrolyte is a substance that when it is dissolved in water, it conducts electricity. So it's a substance whose aqueous solution conducts an electric current. And a non-electrolyte is a substance whose aqueous solution does not conduct an electric current. So we can talk about strong electrolytes and weak electrolytes. So we have non-electrolytes, and then we have strong electrolytes and weak electrolytes. So the strong electrolytes, their solution conducts electricity very efficiently. So there are three major classes of those. Those are soluble salts, because they dissociate completely, strong acids, because they dissociate completely, and strong bases, because they also dissociate completely. Generally speaking, the strong acids are actually the most conductive because the mobility of the hydrogen ion, followed by the strong bases, again, because of the mobility of the hydroxide ion, followed by the soluble salts. And then within the soluble salts, the ones that produce more ions are going to be more efficient conductors as well. So if we were to compare, for example, sodium chloride and calcium chloride, because the sodium chloride, when it dissociates, produces 2 ions, but the calcium chloride produces 3, calcium chloride is actually going to conduct electricity more efficiently. And then our weak electrolytes are weak acids and bases and slightly soluble salts. In these cases, we have some ions in the solution and therefore some ability to carry the electric current, but not as much as if we had a completely soluble salt or a strong acid or base. Okay, so in Honors Chem, you guys learned a lot of different ways of expressing concentration. We learned mass percent, we learned parts per million, parts per billion, parts per thousand. We've just learned mole fraction in AP Chem, molarity and molality. So let's talk about molarity. So just a quick reminder that molarity is the moles of solute per liter of solution. So you learned this one in Honors Chem. Just a quick reminder that because volume is temperature dependent, this means that molarity can change with temperature because that bottom piece, that liters of solution, may change. This is the only unit of concentration you need to know for AP chemistry. So molarity, moles of solute per liter of solution. You have to be able to calculate molarity. So in order to calculate molarity, the first thing we have to do is figure out the number of moles of solute. If we're given the mass of the solute, we're going to divide by molar mass in order to find the moles of solute. And then we're going to divide the moles of solute by the volume of the solution, making sure that that volume is in liters, and that will give us molarity. So let's look at an example problem. So our question asks us, what is the molarity of a solution produced by dissolving 42.5 grams of calcium sulfate in sufficient water to produce 750 milliliters of solution? So you'll notice that we have 3 significant figures here and 3 significant figures here. So the first thing we're going to have to do is convert this 42.5 grams of calcium sulfate into moles of calcium sulfate. We will also need to convert these milliliters into liters. So 42.5 grams of calcium sulfate times 1 mole per 136.14 grams, and we find that we have 0.312 moles of calcium sulfate. We're then going to divide that number of moles of calcium sulfate by the volume of the solution in liters. So we've again converted milliliters to liters, and we find that the molarity of this solution is 0.416 molar. Pretty simple and straightforward. But what if I asked you to calculate the molarity of ions? So just like before, we're going to determine the number of moles of solute by dividing by molar mass. We're then going to divide the moles of solute by the volume of solution in liters to find the molarity of the solute. But now the last step is going to be that we need to convert from molarity of solute to the molarity of the ions. And so that's going to require a conversion factor where we talk about the number of moles of ions per mole of solute. And so it's kind of like a stoichiometry step. We're just converting from moles of solute to moles of ions. So our example problem here asks us what the molar concentration of the sodium ion in a solution that's produced by dissolving 15 grams of sodium carbonate in enough water to make 150 milliliters of solution. So again, our first step is going to be to convert sodium carbonate grams into moles. So we're going to divide by the molar mass to find that we have 0.142 moles of sodium carbonate. We're going to divide that by the volume to find that we have 0.943 molar sodium carbonate. And since molar means moles per liter, we can convert the moles. And we're going to convert from molarity of sodium carbonate to molarity of sodium ions by using the mole ratio that there are 2 moles of sodium ions for every 1 mole of sodium carbonate. And we'll discover that we have 1.89 molar sodium ions in our solution. So again, nothing complicated, just a different application of stoichiometry. Okay, now how do we make a solution? So if we're asked to go the other way, we're given a molarity and we're asked to figure out what mass we need to make that solution. So first we're going to determine the appropriate moles of solute for the given volume. So molarity times volume is going to give us the moles of solute. And then from there, we'll determine the mass of solute that's needed. So the moles of solute times the molar mass is going to give us the mass of the solute. So as an example, what mass of potassium hydroxide should be used to prepare 100 milliliters of a 0.875 molar solution of potassium hydroxide? So first, we're going to multiply molarity by volume in order to find the number of moles of potassium hydroxide. Please excuse the typo. Then we're going to multiply that number of moles by the molar mass in order to find a mass. So we would need 4.91 grams of potassium hydroxide. Okay, So we can make a solution, we can determine molarity. Now, what happens if we dilute a solution? So diluting means adding water to change the concentration, and it's always going to decrease concentration. We know that molarity times volume gives us the moles of solute. Adding water is never going to change the moles of solute. So the number of moles is going to remain the same. The only thing that's going to change is the volume and the molarity. So we can use the equation that tells us the molarity of the stock solution times the volume of the stock solution is equal to the dilute molarity times the dilute volume. Or we can just say M1 V1 equals M2 V2. Because in both cases, we have molarity times volume, which gives us moles, and so that number is always going to be equal to itself. So this is a very common activity in the lab. We take stock solutions and we dilute them down in order to prepare the solutions we need for a lab. So if we want to dilute our 11.6 molar hydrochloric acid down in order to prepare 250 milliliters of 3 molar hydrochloric acid solution, we're going to use that equation. The molarity of the stock solution times the volume of the stock solution will equal the molarity of the dilute solution times the volume of the dilute solution. So we have 3 molar times 0.250 liters, or that 250 milliliters, is equal to the molarity of the stock solution, 11.6 molar, times some volume. And when we solve that for the volume, we find that we cancel out the molarity units and we get 0.065 liters or 65 milliliters. When you're using this equation, you actually do not have to convert to liters. You may stay in milliliters if it's more convenient. Just make sure that you are consistent. Write the units in your equation so that you don't get mixed up. Okay. Now, what if we take 2 solutions and we combine them? So when we combine 2 solutions, we have to account for the factor that we're diluting them. By combining them, we are going to have a larger overall volume, and we need to account for the number of moles that's being contributed from each solution. So in order to do that, we're first going to determine the number of moles of solute in each initial solution, and we're going to add them up to find the total number of moles in the combined solution. So again, molarity times volume will give us moles. We'll do that for each solution and add those up. Then we're going to determine the total volume of the combined solutions. So we're just going to add up those volumes. Usually you'll see a little comment that we would assume that volumes are additive. And then we're going to divide the total number of moles by the total volume to give us the molarity. So let's look at an example. So we're going to combine 35 milliliters of 3 molar calcium chloride with 75 milliliters of 1.5 molar calcium chloride. So this is where you want to think so that you have an ending point in mind so that you can check your own work. When we combine these two, we would expect the final molarity to be somewhere between the two of them. And since we have more of the 1.5 molar calcium chloride, we would expect it to be closer to the 1.5 molar. This is just a self-check point. So first thing that we're doing is we are determining the number of moles in each solution. We're multiplying the molarity by the volume to find the moles, and then we're adding them up. Now, each of these numbers should only have 2 significant figures, but as always, we're waiting until the end of the problem to round. Now we're combining the volumes. We have 35 milliliters and 75 milliliters combining for 110 milliliters. Now this case we're adding, so this number does have 3 significant figures because this 5 and this 5 are both significant, which means that 0 is significant. So we have our total number of moles from this problem divided by our total volume from this problem, and we get 2.0 molar, again, back to two significant figures. And this, if we think about that self-check, we're closer to the 1.5 than we are to the 3, and we are in between them, and so we know that we've done well, and we can circle our answer and move on. Okay. Now we've got to make a solution. So if we want to make a solution, we first have to figure out the number of moles of solute for the given volume, just as we did when we were calculating how to make a solution. We're going to determine the mass of solute that's needed. And then we're going to talk about an appropriate procedure. So if you're asked how you would make a solution, you want to measure out the appropriate mass. You want to add it to the correct size volumetric flask. It's very important when we're trying to make a solution precisely that we know exactly the volume. And so the volumetric flask is always the appropriate choice for making a solution. And then we're going to dilute it to the line and mix. So as a student, how should you prepare 250 milliliters of a 0.75 molar solution of cobalt-2 chloride? First, you need to figure out how many moles of cobalt-2 chloride you need by multiplying the molarity by the volume. That gives you the moles of cobalt-2 chloride. Again, not rounding until the end. We now take that number of moles and we multiply it by the molar mass of cobalt-2 chloride. So 0.1875 moles of cobalt-2 chloride times 98.91 grams of cobalt-2 chloride per mole. And we discover that we need 18.5 grams of cobalt-2 chloride. We're going to then write our procedure that we would measure out 18.5 grams of cobalt-2 chloride, add that to a 250 milliliter volumetric flask, and add distilled water to dilute to the line. Now, technically, this should actually be 19 grams of cobalt-2 chloride, but one would hope that if you're using a volumetric flask, that you would also be given a slightly more precise molarity number so that you would have 3 significant figures and not simply 2. Okay, so now we know how to calculate molarity. We know how to use molarity in order to determine how to make the solutions, how to combine solutions. Let's talk about how we represent solutions. So let's talk about particulate diagrams. These are a particular favorite of College Board. They are our way of picturing the microscopic. So if we look at this first one on the left here, we have 2 different volumetric flasks, one containing a 0.20 molar solution of potassium chloride, and the other one containing a 0.10 molar solution of potassium chloride. So if you are asked to represent 2 different solutions or 2 different concentrations of the same solution, you would want to make sure that your particulate diagram of the higher concentration one contains, well, in this case, since it's twice as many particles. So we're seeing twice as many potassium ions and twice as many chloride ions. Okay, this one is showing a reaction. It is particularly showing a precipitation reaction. We have 2 beakers, each containing a solution, one of sodium hydroxide and one of magnesium chloride. And when we combine the 2, you notice that our volume increases and the magnesium combines with the hydroxide and precipitates out. Anytime we have a precipitate, we want to draw that as kind of a little pile at the bottom of the beaker. And then we still have this dissolved sodium chloride. And we would write this as aqueous in our equation. And so we want to make sure that we still represent it as individual ions. It's really important when drawing particulate diagrams that you represent the ions individually and not combined with each other. And that we represent, if we have 2 chloride ions over here, we need to make sure that we still have 2 chloride ions over here. Now, in a reaction like this one, we would probably be talking about adding sodium hydroxide in excess to ensure the complete precipitation of the magnesium ions. And so we would probably want to draw this with more sodium and more hydroxide, which would then mean over here we would have more sodiums and we would still have some hydroxide that had not combined in with the magnesium because we were only representing one magnesium ion here. And the last thing that's really important to remember about particulate diagrams is that when we draw these, if it asks us to draw the solution, it's really important that you draw them with the proper orientation. So these little Mickey Mouse ears represent our water molecules, and these are our ions. And we're always going to see them with the negative side of the polar water molecule, that's the oxygen side, facing the positive ions, because now we have that ion dipole interaction. And we're going to see the positive hydrogen end of the water molecule being attracted to the negative ions. So make sure that that orientation is correct. Okay, can we separate solutions? Absolutely. Can we separate them by filtration? No. Okay, but we have several different ways that we can separate solutions. One you've done in the lab, and that's paper chromatography. There are lots of different forms of chromatography. There's thin layer chromatography, there's high pressure liquid chromatography. Paper chromatography is certainly the most accessible in a high school classroom. And the way that chromatography works is that there are two competing attractions. The substance to be separated is going to be attracted to the mobile phase, that's the solvent, and to the stationary phase. In the case of paper chromatography, that's the paper. The more similar the intermolecular forces are to the intermolecular forces in the solvent, the farther and faster your substance is going to travel. And so that means that if your substance is very polar, and I would say that this particular marker was more polar, or this particular ink or dye was more polar, because it's moving less quickly or has not moved as far. Here we can see that the dyes in this ink actually separated. The blue is traveling faster than the yellow. And so that tells us that the blue is probably less polar. I'm assuming this is a non-polar solvent. And the yellow is more polar. So what that means is that the more polar one is more attracted to the stationary phase, the paper, and the less polar one is more attracted to the mobile phase, or the solvent. All chromatography works on the same principle, the difference between the attractions to the solvent versus the attractions to the stationary phase. There's also distillation as a separation technique. Distillation relies on differences in boiling point. And so by heating our solution, the substance, the component with the lower boiling point, is going to boil off sooner. It's going to be condensed in this condenser phase and collected over here in the receiving flask. We can do sequential distillations. So by reaching the boiling point of first one component and collecting it, and then continuing to heat and collecting a second or even a third distillate, we can separate a mixture completely. This is how crude oil is separated into its components, is by fractional distillation. Okay, we can also separate a mixture by crystallization. This can be as simple as cooling a saturated solution to the point where the solute starts to crystallize out and then collecting those crystals, or we can actually use differences in solubility to separate two different solutes. So if one is more soluble at low temperature than another, then we can cool it to that particular point, separate out the one with the that requires more heat to be dissolved, and separate out the one that will then stay in solution. So I know I said that we can't separate them by filtration. We cannot if it's all still in solution. But if by crystallizing out one of the solutes, then we can filter it out. Once it's crystalline, it's not actually in solution anymore. And then the simplest one is evaporation. So this only works if we have a non-volatile solute. But if, for example, we had a ionic compound in water, then we certainly can evaporate off the water and collect the solute. So this is evaporating to dryness. We're just heating the solution until all the solvent evaporates. Okay, so I know that's a lot of information, but much of it is review. So as always, if you have any questions, please let me know.